Welcome back to the deep dive. We're diving into object detection today, looking at how these models have evolved to
It's
see
really
and
fascinating.
understand the world.
Yeah, it's a story of remarkable progress, really. Starting with those early models that processed information step by step.
Almost like reading a book word by word.
Yeah, exactly.
So we're talking about recurrent neural networks, or
Yeah,
RNNs.
yeah. RNNs.
I remember hearing about them.
Yeah.
But how do they actually work when it comes to seeing objects?
Well, imagine an RNN kind of scanning an image pixel by pixel, trying to make sense of it one tiny piece at a
So
time.
it's like,
And while this approach can work, you
yeah,
know,
yeah,
it's inherently slow, especially when you're dealing with high-resolution images,
yeah,
with millions pixels.
yeah. That's got to be a bottleneck.
Right.
It's like trying to understand a picture by looking at every individual grain of sand.
Precisely. And that's where the concept of attention comes in.
Okay.
It's a game changer, really, because it allows models to focus on the most important parts of an image,
Yeah.
much like our own eyes, darting around a scene.
Okay, I'm starting to get the picture.
Yeah.
But how do you teach a computer to pay attention in the same way humans do?
Well, instead of, analyzing every single pixel attention-based models, learn to identify key regions or features that are most relevant for detecting objects.
Yep.
Think of it like reading a book and focusing on the key sentences that, reveal the plot.
So the model's learning to skim the image,
Right.
picking out the most important bits
Yeah,
without getting bogged down in the details.
exactly. And this ability to selectively focus attention leads to significant improvements
Yeah,
in both speed and accuracy.
that makes sense. By focusing on the most important information, the model can process things much faster
Right.
and avoid getting distracted by irrelevant details.
Yeah. And this shift towards attention-based models was a major breakthrough, and it led to the development of a revolutionary architecture called the transformer.
Ooh, I've heard of transformers.
Yeah.
They're the powerhouses behind those impressive language models.
Right. They are. The papal attention is all you need introduced the transformer, a model that relies entirely on this attention mechanism, ditching the sequential processing of RNNs altogether.
Wow. So instead of processing information step by step, the transformer can analyze an entire image or sentence in parallel, focusing on the relationships between different parts.
Exactly. And this ability to capture those relationships, those long-range dependencies in the data, was a major limitation of RNNs.
So the transformer's ability to see the big picture is
Yes.
what makes it so powerful.
Precisely. And this power translated incredibly well to the world of object detection, leading to the development of the DETR model.
DTR. What does that stand for? How does it use the transformer's attention mechanism to find objects in images?
DETR stands for Detection Transformer, and it applies the transformer's architecture to directly predict a set of objects in an image.
Okay, so instead of analyzing the image sequentially, it's using attention to identify all the objects simultaneously.
Exactly. And this direct prediction simplifies the entire object detection pipeline compared to traditional methods that relied on a complex multi-step process.
Wow. So it's more streamlined and efficient.
Much more.
Can you give me an example of how this actually works in practice?
Sure. Imagine you're trying to detect cars in a street scene. Traditional models might first generate hundreds of potential bounding boxes, then analyze each one to see if it contains a car.
Right.
This process is computationally expensive and can lead to false positives.
Still a lot of wasted effort chasing down those phantom cars.
Exactly. DETR, on the other hand, uses attention to directly predict the final set of bounding boxes, eliminating those extra steps and reducing the chance of errors.
That's a huge improvement.
It is.
It's like having a detective who can instantly spot all the suspects in a lineup without having to go through each one individually.
Precisely. And this efficiency was particularly evident in tasks like panoptic segmentation, which involves labeling every single pixel in an image.
Panoptic segmentation. Sounds intense. How does DETR handle such a detailed task?
Well, panoptic segmentation requires understanding not just the objects themselves, but also the stuff classes, like the skygrass or road.
So it's like creating a detailed map of the entire scene, identifying both the distinct objects and the background elements.
Exactly. And DTR's ability to capture global relationships, thanks to its attention mechanism, made it surprisingly good at handling these stuff classes.
So DTR was a major leap forward, but I imagine there were still challenges to overcome.
You're absolutely right. One of the main hurdles was speed, especially when dealing with high-resolution images. And that's where deformable DETR comes in.
Okay.
It takes the core concept of attention and refines it, making it even more efficient and powerful.
Okay, I'm intrigued. How did they manage to deform attention to make it better?
Well, imagine our eyes darting around a scene, but instead of focusing on every single point, we selectively attend to a few key regions that stand out.
Okay.
That's the essence of deformable attention.
Okay.
It learns to focus on a smaller set of points rather than attending to every single pixel in the image.
So it's like giving the model a magnifying glass, allowing it to zoom in on the most important details.
Exactly, and this focused attention drastically reduces the computational cost, making deformable DETR much faster than its predecessor, especially when dealing with those high-resolution images.
That's impressive. And this deformed attention, did it impact accuracy in any way?
Not only did it speed things up, but it also boosted accuracy, especially when it came to detecting those small, easily missed objects.
So faster, more accurate, and better at finding those tiny objects.
Yeah.
It sounds like deformable DETR really hit the sweet spot. But before we get too carried away, let's take a step back and remind ourselves why we're on this journey in the first place.
You're right. It's about more than just building faster and more accurate models. It's about pushing the boundaries of what computers can see and understand. It's about creating a new era of visual intelligence.
That's a powerful thought. And as we'll see in the next part of our deep dive, this quest for visual intelligence is leading to some truly remarkable breakthroughs. Stay tuned. We've been talking about how these object detection models, have evolved to become faster and more accurate. But I'm curious about the driving force behind this progress. Is it all thanks to the transformer architecture, or is the attention mechanism the real game changer?
Well, while the transformer architecture popularized attention, it's essential to remember that attention is a concept that can be applied in various ways, even beyond the transformer framework.
So it's like attention is the underlying superpower, and the transformer is just one tool for harnessing that power.
Yeah, a good analogy. There are other models that incorporate attention without using the full transformer structure.
That makes sense. But for object detection, the combination of transformers and attention seems to be the winning formula. Are there other areas where researchers are pushing the boundaries within this winning formula?
One area of active research is the refinement of object queries. In models like DETR and deformable DETR, these queries guide the model's attention to potential object locations.
So they're like scouts sent out to explore the image and find objects.
Yeah. In the original models, these queries were generated randomly without any prior knowledge of the image content. Researchers are now exploring ways to make those queries more informed, giving them a better starting point.
So it's like giving those scouts a map and some hints about where to look. How do they make these queries more informed?
Well, one method involves using region proposal networks, or RPNs. These are smaller neural networks trained to quickly identify potential object regions in the image.
So it's like having expert map makers highlight the areas where those scouts should focus their efforts.
Right. By using RPNs to generate more informed object queries, researchers can speed up training and improve overall accuracy.
Makes perfect sense. The less time those scouts spend wandering aimlessly, the better. Are there other strategies for making object queries smarter?
Another exciting direction is learned object queries. Instead of fixed predefined queries, researchers are experimenting with models that learn to generate queries specifically tailored to the objects they're looking for.
So it's like those scouts can now train and specialize, becoming experts in finding specific types of objects.
Yeah. This ability to learn and adapt queries has the potential to further improve the efficiency and accuracy of object detection models.
It's like having a team of highly specialized detectives, each with their own unique expertise. We've talked a lot about the technical advancements, but how are these improvements being applied in the real world?
Well, object detection is having a significant impact in various fields. One prominent example is autonomous driving.
Right. Self-driving cars need to see and understand their surroundings, and object detection plays a crucial role.
Yeah, object detection models are used to identify and track other vehicles, pedestrians, traffic signs, and obstacles. They provide the car with a set of superpowered eyes to navigate the complex world of roads and traffic.
Beyond autonomous driving, what other domains are benefiting from these advancements?
In healthcare, object detection analyzes medical images, helping doctors detect tumors, diagnose diseases, and plan surgeries more effectively.
It's like having a second opinion, helping doctors see things that might be missed by the human eye.
Yeah. And in security, object detection monitors surveillance footage, identifying suspicious activity, tracking individuals, and enhancing overall safety.
It sounds like these models are becoming essential tools across various industries. It's incredible to see how far we've come. But as with any powerful technology, there are ethical considerations we need to be mindful of.
Right. One concern is the potential for bias. If the training data itself contains biases, those biases can be amplified by the model, leading to unfair outcomes.
So if the data used to train the model is skewed, the model's decisions might also be skewed.
Yeah, researchers and developers are actively working to address this issue. They're striving to ensure that models are trained on diverse and representative data sets to mitigate the risk of bias.
So it's not just about making these models faster and more accurate, it's also about making them fair and unbiased.
Yeah, we have a responsibility to develop these technologies in a way that benefits all of society.
That's a crucial point to keep in mind as we continue to push the boundaries of what these models can do. But there's one more key development we haven't touched on yet.
You're right. We haven't yet explored the world of multimodal learning. It's the idea of training models to understand information from multiple sources, not just images.
Multimodal learning. So instead of just analyzing images, these models can integrate information from text, audio, and other sources.
Precisely. By combining these different modes of information, these models can make more accurate and nuanced predictions. It's like giving them extra senses to perceive the world in a more holistic way.
That sounds incredibly powerful. But how does multimodal learning work in practice?
Well, one common approach is to use separate encoders for each modality, processing the images, text, and audio independently. Then those encoded representations are combined into a single unified representation.
So it's like having a team of specialized experts, each analyzing their own piece of the puzzle, then bringing all those insights together to form a complete picture.
A great way to put it. This multimodal approach is proving particularly effective in tasks like image captioning.
Image captioning. So these models are not only identifying objects, but also describing them in words.
By combining visual information from the image with linguistic knowledge from text, these models can generate accurate and descriptive captions that capture the essence of the scene.
It's like they're learning to not only see the world, but also talk about it. This multimodal learning seems like a real game changer. It's like we're moving beyond teaching models to see or hear. We're teaching them to truly understand the world around them.
Yeah, it's a fascinating area of research with the potential to revolutionize a wide range of AI applications from robotics to natural language processing.
I can only imagine the possibilities. We've covered so much ground from the fundamentals of object detection to cutting-edge advancements like multimodal learning. But before we wrap up, let's provide our listeners with some guidance on how they can delve deeper into this exciting field.
A great idea. For those starting to explore object detection, there are a few fundamental concepts and resources worth knowing.
Let's break it down. What's the first thing someone new to this field should understand? Okay, so we've got these amazing models that can find objects in images. How do we even categorize those tasks? It can't all just be object detection, right?
Yeah, you're right. It's helpful to think of it as levels of complexity. The most basic is image classification, figuring out what's in the picture as a whole, like labeling it cat or dog.
Simple enough. But what about when there are multiple objects, like a busy street scene?
Right, that's where object localization comes in. We need to identify each object and pinpoint where it is, usually with a bounding box.
So it's not just what, but where. Then object detection itself is taking that further, finding all the objects in a complex image.
Exactly. Each level needs different approaches and models. And of course, the ones we've been discussing are on the cutting edge of that complexity.
For listeners wanting to learn more, where should they start? Those papers we mentioned sound intimidating.
Yeah, the Attention is All You Need paper is the foundation explaining the transformer and attention itself. But AI is dense.
Makes sense, given it revolutionized the field. What about actually building these models?
Well, PyTorch and TensorFlow are the go-to platforms. They've got the tools to implement and experiment, plus tons of online tutorials to help.
So there's support out there, even for beginners who want to try this stuff out. That's encouraging.
Absolutely. The community is huge and growing rapidly. There's always something new to learn and discover in this field.
This has been an incredible journey, from basic concepts to these mind-blowing models like deformable BETR and even multimodal learning. It's clear object detection is more than just drawing boxes on pictures.
It really is. We're at a point where computers aren't just seeing, but starting to understand.
What's the one key takeaway you'd leave our listeners with today?
The field is constantly evolving. What seems cutting edge now will be surpassed soon enough. But the core idea, teaching machines to see the world, that's only going to become more important.
And with that evolution comes the responsibility to use this technology wisely and ethically, as we've discussed.
Couldn't agree more. The future of object detection is bright, but it's up to us to guide it in a direction that benefits everyone.
So to our listeners, keep those minds curious. Keep exploring, and remember, the future of AI is in our hands. Until next time, keep diving deep.